Okay, let's continue. Let's go to the next chapter. The next chapter is going to be rotation of rigid bodies. Right, in this case, let's go to rotational kinematics. Okay, let's do it. Let's compare first the linear case and the rotational case. Okay, for example, this is the linear motion and this is the rotational, right, motion. Okay, remember how we started studying linear motion? Well, we started with a reference frame, right? The observers right here, right? The same 1D for simplicity. This is x direction, right, in meters, and then we went for the units, right? Let's do the same thing in rotational motion, correct? We have the circular path, rotational path, right? We need the reference frame. This is my 0 position, right? And then let's go to initial position, right? Imagine, right? And final position in linear case. Let's do the same thing in the rotational case, correct? Let's go to the initial position, correct? And final position. The symbol for a linear case is X. For a rotational case is theta, right? Theta initial right here and theta final, correct? Now, what's next right here? The units, right? What is the unit that we use for rotational motion? Well, we use meter. What about in the rotational motion? What should be the unit? Well, the unit could be degrees, right? Degrees could be radians or radian, correct? Those are the units. Now, let's go for the displacement. How do we define displacement in the x direction? Is equals to final position minus initial position. Let's do the same thing in the rotational case, right? The displacement, right, angular displacement is defined as final angle minus initial angle, right? Similarly to this one. Perfect. Now let's go to the velocity, right? How do we do it? Well, we divide this displacement, right, in x respect to time, correct? Respect to time, perfect. And this is what? Velocity. Because this is a big time, we call this the average velocity. The safety happens right here, correct? So we need to divide this angular displacement by the time. When we do that, we create a new quantity and we call this the angular velocity. The symbol is omega, right? That's angular velocity. Angular velocity, correct? And the unit, what should be the unit for this one? Unit, right? The unit for theta is gonna be radians, right? Radians, and the unit for time is gonna be second. So units of omega is radians per second, correct? Now let's go to acceleration. Remember, how do we define acceleration for the linear case? Well, we say that acceleration is just equals to change in velocity, correct, respect to time. They do the same thing for rotational acceleration. So we have that the change in omega, right, respect to time is equals to the rotational acceleration, and the symbol is alpha, right? So this is rotational, right, acceleration. Perfect. What should be the units for this new quantity? Well, units are, right, radians per second square. Those are the units for alpha, the angular acceleration. Great. Now let's see what happens when we're dealing with motion. Remember, we're in kinematics. Kinematics describes motion. How we did it for linear case? Well, we used the kinematic equations. Now we can do the same thing for rotational motion. Remember, kinematic equations are valid only if acceleration is constant. Imagine that this acceleration is constant. Also, we can use kinematic equations for rotational motion. Let's do it. For linear case, remember, we found that the final velocity equals to initial velocity, right, plus acceleration times time. Also, we found that the displacement in the x direction is equals to initial velocity times time plus, right, 1/2 acceleration times t squared. Also, we found that v squared, right, final is equals to initial velocity squared, right, plus twice the acceleration times the displacement. Well, because this is constant, we can do the same thing when alpha is constant. Let's do it. So they have the same form, right? So gonna be omega final equals to initial omega, right? Angular velocity, right? Plus what? Alpha times time. This one, the next one's gonna be angular displacement is equals to, right, initial velocity times time plus 1/2 alpha t squared, correct? And finally we have final, right, angular velocity. Oh my god. Okay, final, right, angular velocity squared is equals to initial angular velocity squared, right, plus twice alpha angular displacement, right? So we can use these formulas to find, right, angular displacement when we deliver rotation, to find final angular velocity. We have time, we have alpha, or the quantities, the same thing as we did for linear cases, correct? Okay, great. Now let's see what happens to again motion when we're dealing with linear case. Remember, we said that to the right, motion to the right is positive and to the left is negative. The same thing happens right here, right? If we are going clockwise, right, the direction is positive, right? Counterclockwise is gonna be negative. That's the convention that we use for directional motion. Okay, perfect. Now let's go to the next concept right here. The next concept is gonna be the relationship between linear quantities and angular quantities. Okay, let's do it. But before that, remember we said that we have this type of units for one revolution, right? For one revolution, we can call this 360 degrees, correct? Or we can call this 2 pi radians, or we can call this, right, 1 revolution. So 1 revolution is equals to 2 pi radians, or equals to 360 degrees. We can use this as the units for, right, rotational motion, right? But let's see what happens. We have actually, when we are working with some calculators, right, we have some units like this one, right? These are degrees, right? Degrees, right? We have another unit called grad, right? Grads right here, grad, right? And we have radians right here, right? Another unit, radians right here. Perfect. How many degrees do we have in this case? Well, we have 360 right here. In some countries still use, right, instead of 360, 400, right, let's say degrees or grads right here. And right here is 2 pi. Okay, 2 pi what? 2 pi radians, correct? So that right here is grad, right? Grad. Perfect. Okay, now, why 360? Well, this is an arbitrary number, maybe because it's related to the time, right, of the Earth moving around the Sun in 1 year, right? Remember, it's what, 365 days, correct? But 365 is not a good number. A better number is 360, the closest one, because this could be divided by 2, by 3, by 5, by 10, like too many numbers, right? So it's a better number than this one. Right here, some quantity says, well, let's round it. Let's round this quantity, this amount, to 400 and should be easier, right, instead of using 360. What about this one? This one is coming from the circumference, right? We have the circumference, and we know that the circumference is equals to 2 pi, right? The radius, correct? What happens if we divide this by radius? We have 2 pi, right? So we have that the ratio of two quantities gives us a constant, and in physics, as you know, every time we have a quantity that is constant, that quantity is very, very important. So this quantity is very important because it's coming from nature, right? From the circumference. This is not arbitrary, right? Arbitrary numbers like this one. It's from geometry. It's very powerful, right? Mainly in this chapter, we are dealing with this unit, right? Radians, because of that. Okay, great. Now, let's go to the next topic, right? The next topic is the relationship between linear quantities, right, to the angular quantities. For example, imagine that we have this circumference, right? We have the radius, and r we have angle theta, and we have this length, right? S, also called the arc length. Okay, how are these three quantities related? Well, they are related in this way. This S is equals to R times theta. Theta must be in radians, right? Now, what happens if we divide S by R, the radius, right? This equals to theta in radians. Okay, what happens if these two are the same, right? If, right, S or R equals to S, what do we have? We have then that theta is equals to 1. 1 what? 1 radian, right? So 1 radian again is the angle formed when this S and R are equal, correct? Okay, perfect. Now let's start with this definition, correct? S equals to R theta. And now let's divide, right, S by time. If we divide S by time, we have to do the same thing, right, to the other side, right, by time. We know that S is the distance. Distance divided by time is speed, right? Speed. What should be this one? Theta divided by the time is omega, right? So this is just omega. So what do we have? V is equals to R times omega, right? So that's the relationship between linear quantity and angular quantity when we're dealing with velocities. Let's do the same thing for acceleration, right? Remember, how do we define acceleration? Acceleration is changing velocity, correct, respect to time. Let's do the same thing, but now let's involve the angular quantity, right? So what do we have? Acceleration is equals to change of velocity, but velocity is just what? R omega, right, respect to time. But R is constant. We can take it from this parenthesis and put it outside. So what do we have then? That acceleration is equals to R, right, changing omega respect to time. But what is this changing omega respect to time? Is just alpha, right? Alpha, the angular acceleration. Great. So what do we have then? We have that acceleration is equals to R times alpha. Right. So this is gonna be the relationship between, again, linear quantities, angular quantities. We have velocity or omega, right? Acceleration or alpha. Okay, great. Now, it's also found that when the angular velocity is constant, right, and we have the angular velocity is just changing omega respect to time, right? When again omega is constant, means that the time for each revolution is the same. We can say that this motion is periodic motion, right? When that happens, right, for one revolution, theta is 2 pi radians, right? And the time for one revolution is 1 period, right? 1 period. So we can say that Omega is equals to 2 pi radius divided by the period when omega is constant. But also we can use another quantity, right? Frequency is defined as 1 over the period. Right, when we use this quantity right here, what do we have? Well, we have that omega is equals to 2 pi frequency, right? This is another very important equation that we have in this chapter. Omega equals to 2 pi the frequency. Omega then is also called the angular frequency because of this frequency. Correct? Okay, now let's go to energy. Okay, let's go to the rotational kinetic energy. Okay, let's do it. Let's do it. Imagine that we have a particle by moving a circular path, right? This is a particle M, right? Imagine it's moving right in this way, correct? In a circular path. Also, at this position, right, we have some velocity. For this particle, how do we define the kinetic energy? Well, we know that kinetic energy is equals to 1/2 mv squared. Now let's involve the rotational quantities to create the rotational kinetic energy, right? So rotational kinetic energy is equals to 1/2 m. Remember what should be velocity? Velocity is equals to r. This is r, right? The radius of the circumference times omega. When we plug this value right here, what do we have? This is r omega squared, correct? So what is this then? It's equals to 1/2 m r squared, right? Omega squared. Now, when we compare these two equations, this is 1/2, this is 1/2, this is velocity squared. Now this is mass, and this is also mass times something right here, times the radius squared. One of the definitions of mass, right? How we can define mass in mechanics? We can define it as the resistance, right, to change velocity, right? That should be mass. How much mass is an object is how much resistance this object has to change its velocity. So we can apply the same concept right here, right? We can define this quantity, right, in the same way as we did in mechanics, right, for mass, correct? And we call this the moment of inertia, right? Moment of inertia is equals to m/r squared. This is a definition, moment of inertia, moment of inertia. Okay, great. This is when, again, we have a particle. Now what happens if we have a bunch of particles, right, moving around the same axis of rotation? Let's do it. What happens in that case? Well, in that case, we have that this rotational motion is equals to, they have the same form, right? 1/2, right? But now let's make the sum of all these particles, right? All the particles right here, right? Moving around, right? The same axis of rotation, correct? So it's equals to 1/2, right? The sum of these all individual masses right here with the individual distances through the axis of rotations, right? In this way, correct? What else? Square, correct? The square times omega initial square, correct? But if they have the same angular velocity, the same omega, we can write this in this way. It's equals to 1/2 the sum m sub I r sub I square, right, times omega square, correct? And this have the same form, right? For a bunch of particles, then we can define that omega inertia equals to the sum m sub I, right, r sub I square. Now, what happens if we have a solid? If we have a solid, right? If we have a solid like a disk, right? we have a solid, right? Imagine this is the disk right here, correct? We have a particle right here. This is m sub I, right? Or a small particle, right? The m, correct? And this is r sub I. So what should be then the moment of inertia? Well, the moment of inertia, right, is equals to the integral times r square dm. Right? This for solid, this for a bunch of particles, it's only for one particle moving right to one x rotation. Okay, one more time. What is the meaning for this moment of inertia again? Is the resistance of an object to change its rotational velocity. Right? For example, imagine that we have a mass, an object, right? All right, this object right here, and we want to rotate it through this x rotation, right? That goes to its center of mass, correct? So like in this case, this one, so it's very easy to rotate it in this way, right? The x rotation is parallel in this case to the object, right? But what happens? It is in this way, right? In this way, where it takes right more inertia, the inertia increases for rotation, right? The resistance increases, correct? So we have again this situation right here, right? When we rotate it in this way, of course, it has more resistance to be rotated than in this case. The mass is the same, but the x rotation is different. Or we can say the distance, look, because we have r squared, right? R squared right here, right? The distance of the mass to the axis of rotation increases respect to this one, right? This is x rotation. All the masses are very close, so r is very small compared to this one. So right here it has more resistance to be rotated, this object, than in this case, right? That's the meaning for this moment of inertia, right? Resistance of the object to change its velocity, correct? Okay, later in the next video, I'm gonna work with moment of inertia for solids, right? We have cases, different cases, like we can use the parallel axis theorem, right? Or we can use the perpendicular axis theorem, right, and so on. So see you in the next video for moment of inertia. Okay, bye.